Alright students, today we are going to talk about a very important topic in biopharmaceutics and pharmacokinetics, that is drug excretion. In simple words, drug excretion means the removal, irreversible removal of drug and its metabolites from the body. Why is this important? Because how a drug is excreted will decide three things. First of all, how long it stays in the body, its duration of action, and even whether the drug could cause toxicity if it gets accumulated. Polar versus non-polar group. So, polar means water soluble drugs easily excreted. Non-polar lipid soluble drugs not easily excreted, they need to be metabolized first into polar forms. For example, most lipid-soluble drugs undergo metabolism in the liver before excretion. There are two broad routes of drug excretion: renal excretion and non-renal excretion. Renal excretion, this is the major route for most drugs. Non-renal excretion, smaller amounts of drugs are eliminated through other pathways like bile, feces, lungs, sins, milk, saliva, etc. But always remember that majority of drugs and their metabolites are excreted from the kidneys only. Okay, so the primary excretion organ is kidneys, but in some cases other routes are also followed, like for example, like anesthetic gases, the lungs play the main role. Now let's move on to the concept of clearance. In that we will be discussing four things: clearance, total systemic clearance, organ clearance, extraction ratio. Let's see the clearance. It is the hypothetical volume of body fluids from which a drug is completely removed per unit time. Units are ml per minute or liter per hour. Its formula is clearance equals to rate of drug elimination divided by drug concentration in plasma or plasma drug concentration. But remember, this does not mean the body fluids are actually emptied of drug. It's just a mathematical way to describe the efficiency of elimination. The concept of drug clearance can be applied to the whole body or from different organs of the body. The mainly organs involved in the drug clearance are lungs, kidneys, liver, skin, intestine, etc. So the calculation will be for hepatic clearance. CLH is equals to rate of elimination through kidneys divided by C, and for renal clearance, rate of elimination through kidneys divided by C, and for others clearance is equals to rate of elimination from other organs divided by C. The total systemic clearance is the sum of all hepatic clearance, renal clearance, and clearance through other organs. So overall clearance represents the body's ability to eliminate the drug. So mathematical expressions are, now we know that dx by dt equals to kex. So we are substituting it. CLT equals to, CLT equals to x by c into ke. Now x by c, we can write it as a Vd. Vd equals to x by c, we know. So our equation becomes CLT equals to Vd ke. In place of ke, we can write it as 0.693 divided by t half. How? Because elimination half-life equals to 0.693 divided by ke. So T half goes here and Ke goes to the left hand side. So our equation becomes CLTVD 0.693 divided by T half. It applies same to the CLR, renal clearance and hepatic clearance also, where T half will be excretion T half and T half here in hepatic will be the metabolism half-life. Now this formula is very useful if we know VD and T half. We can calculate clearance without directly measuring elimination. Let's focus on organ clearance. The rate of elimination of a drug from a particular organ is known as organ clearance. We can also say it as the rate of elimination of a drug by a particular organ. And we also know that rate of entry of a drug into organ is more than the rate of its exit from the same organ. Now, how to calculate it? Rate of drug entry equals to organ blood flow, which is represented by Q, into entering drug concentration, CIN. C means concentration, N means entering. So in short, QCIN. Let's see the rate of drug exit. Organ blood flow, Q, exiting drug concentration, C out, Q, C out. Rate of elimination. Rate of drug entry minus rate of drug exit, Q sin minus Q C out. We can take it common, Q, and write it in bracket Q C CIN minus C out. Let's see the extraction ratio, ER. It tells us how efficient an organ is at removing a drug from the blood. Its formula is ER equals to Q C in minus C out divided by C in. Its value ranges from 0 to 1. ER has no units. It's a ratio. Let's see the drugs classification based on ER values. First one, we have high ER. When we say if the value comes more than 0.7, drug is efficiently removed. Example, propranolol, morphine for hepatic and for renal penicillins. For intermediate extraction ratio, we say 0.3 to 0.7. If the value ranges from in this between 2, we can say partial removal of drug. Drugs like aspirin, codeine, cimetidine. For lower extraction ratio, the value should be less than 0.3. Example of drugs, phenytoin, digoxin, atenolol. We can say poorly removal of drug. So if ER is high, drug clearance depends mainly on blood flow to the organ. If ER is low, clearance depends more on the organ's metabolic capacity. So in liver disease, clearance of high extraction drugs drops because blood flow is reduced. In renal failure, clearance is of renally excreted drugs like aminoglycosides decreases, causing accumulation and toxicity. So doses adjustment is often needed based on clearance. What are the points to be noted? They are drug excretion. It is irreversible removal of drugs metabolites. Then kidneys. They are the major route and non-renal routes also exist. Next, clearance. It is the efficiency of elimination. It is measured in ml per minute or liter per hour. Then we have seen total clearance. It is the sum of renal, hepatic and other clearances. Next we have seen organ clearance and extraction ratio. It helps us to understand how effectively a drug is cleared by each organ. In short, excretion is how the drug leaves the body, clearance how efficiently the body removes it. Both are fundamental concepts in pharmacokinetics and are essential for understanding dosing, drug accumulation and safety.